All right, welcome back everyone. Let's go over the solution to the now you try problem on translating an application into a symbolic form for a function, how to get a graph of that function, and then how to answer some questions about the scenario using that function. Let's jump right in here. The problem says to assume a tree grows at a constant rate. When the tree was planted, it was 2.1 feet tall. After 10 years, the tree grew to 8.1 feet tall. We're going to start by determining the symbolic form for the function, modeling the height of the tree given a certain number of years. So let's just make a quick table of values here. We have at time 0, when we first plant the tree, it's 2.1 feet tall. And then let's name this h of t for height. And so after 10 years, the tree is now 8.1 feet tall. So we can see the y-intercept is 0, 2.1. And then we see the slope is going to be 8.1 minus 2.1 divided by 10 minus 0. It's going to be 6 over 10. And we can reduce that to 3/5. So with this, we can put that together and say that the height of the tree, h of t, equals 3/5 t plus 2.1. Let's be careful to note that the output is the height, and that's in feet, and the input is time in years. And let's see, we want to know what is the height. Before I actually graph this, I'm going to answer these other questions. It says, what is the height of the tree after 50 years? So if I say h of 50, 50 is a time, so I can plug that into the function. We'll get 3/5 times 50 plus 2.1. So the 5 and the 50 can reduce to a 1 and a 10. So we'll get 30 plus 2.1 is 32.1. So in 50 years, the tree is 32.1 feet tall. And we want to know, when does the tree reach a height of 68.1 feet? So I can set h of t, the height, equal to 68.1 feet, and we want to solve that equation. So we'll put in the 3/5 t plus 2.1 equals 68.1. And we'll subtract the 2.1 from both sides to get 3/5 t equals, the 0.1s will cancel, 68 minus 2 is 66. And then I'm going to multiply both sides by 5/3 to cancel these fractions. The 3's cancel, the 5's cancel. And we will get t equals, on the right side, we can reduce a bit here. 66 can become 22, while the 3 becomes a 1. So we'll get 22 times 5. That's 110. So the tree will be 68.1 feet tall in 110 years after being planted. All right, so with this, we can start to see that we've got some pretty big numbers here. So I'm actually going to do this graph. I'm going to just Now, I'm not going to go backwards in time, and I'm not going to we don't have any negative heights to worry about, so I'm going to reorganize this so that the origin is in the bottom left-hand corner instead of in the middle. We've got time for our horizontal axis, and then h of t for our vertical axis. And the height gets pretty big, right? We're looking at 68.1 feet there. So let's do like, check how much I've got here. Let's say that's 10. Let's make that 15, 30, 45, 60, 75, 90 for our heights there in feet. And then time, we're looking at 110 years to get to 68.1. And I'm actually noting in part E, it says, supposing the tree dies after 170 years, determine the domain and range of the function in context of this scenario. So the time that we want to look at is 170 years. So if I go and say, that's, oh, it keeps happening. 40 years, 80, 120, and 60. That's not a bad scale. All right, so we know when we first plant it, it's just a little sapling. It's 2.1 feet tall. That's going to be right down in here. Right, these are by 5, so it's a little less than the halfway point there. We know that after 50 years, it has gone up to 32.1 feet tall. So we go to 50, and I'll go up to 32.1 is about here. We also know that at 110 years, it's going to be 68.1 feet tall. Let's go ahead and get that in there. So here's 65, 67, 68.1 is about in here. And then 170 is when we want to stop this. This is going to put a little vertical line here where the 170 is, so I know when to stop drawing my line. I'm going to go ahead and get a ruler out for this, because it's going to be a tough one to keep straight. It's pretty good. Go. And we know it dies at that point. Really, at that point, it would continue on at staying at that height until it gets cut down or falls, but we'll just stop this function right there at that point. So here we have h of t equals 3/5 t plus 2.1. So now we've got our graphical form, and we can now look at our domain and our range. So the domain's pretty straightforward here. We can see this. The domain starts when we plant the sapling at 0 years, and it goes up to 170 years, and then stops. The range, we need to do a little bit more work here, because I don't know how tall it is at 170 years when it dies. So let's go ahead and say, what is h of 170? So I'll plug 170 in here, 3/5 times 170, and we'll add 2.1 to that. So let's see, 5 into 170. 5 goes into 120 times, and then up to 150 would be another 10, so that's 30 to get to 150, and then 4 more to get to 170. So that's comes to 1. 170 is over 1, so that's how I'm reducing here. What did I just say? 34. So then we'll go 3 times 34. That is 90 plus 12, that's 100. And 2 plus 2.1 equals 104.1. And I'll go and label that here. That's 170, comma 104.1. So the range is 2.1, its height when we first plant it, up to 104.1 feet tall when it stops growing. All right, there we go. Thanks much for watching. And in the next video, we are going to go over, let's see what it was. Okay, so we're going to switch topics a little bit in the next video. It's still part of the same lesson that you need to watch before next class, but we're going to go into using functions symbolically and in applications where we kind of look at plugging in some things other than just a basic number, but another expression into a function or multiplying a function by a number. So go ahead and check that out when you're all set here, and I'll see you in that video.